Section 4.1, we're going to talk about extrema on function. So I think extrema is plural of Latin for like extreme is in terms of extreme values. We're going to want to find the extreme values on a function, and it's going to start with the definition of something called critical points. Now on the graph here, I've labeled a couple of interesting points on this graph. If you had to characterize critical points, how would you define critical points? Using calculus, how would you define what it means to be a critical point? Something that would encompass all these points A through F. Derivative equals 0 or does not exist. Good. So one of two things is happening at a critical point. Now these critical points are interesting places in a function, right? What's happening at critical points in this function? Yeah, you got a local max or a local min. Something interesting is going to happen at these points. So critical points are places where f prime of x equals 0 or f prime of x does not exist. So those are critical points. Part of our earlier work here is going to be to define critical points, and then we're going to work on finding the extreme value of a function over an interval. It's going to start by looking at where are the critical points. So let's first start by finding some critical points. We'll begin with problem number 14. Problem 14 is on your handout. So how many critical points do you think we should end up with if we tried to find critical points for problem number 14? Yeah, it looks like 2. All right. So let's see if that works out for us. Problem 14, f of x is 4x over x squared plus 1. To find the critical points, we've got to take the derivative and set it equals 0 or figure out where the derivative doesn't exist. Now, it's not a bad idea beforehand to look at the function and try and think about the domain of the function. Are there any values of x for which f of x is undefined? No. That wouldn't be true if this was a minus in the denominator. If there was a minus in the denominator, then it would be a much different story. But we've got a plus there, so let's work on the derivative. Calculating the derivative means we have to use our favorite rule, the quotient rule. Good job, all in unison there. So let's see if we can't calculate f prime of x. Do you need me to write out the f and g and stuff like that? Are we good on that? All right, let's start with the square of the denominator, x squared plus 1 squared. And then the denominator again times the derivative of the numerator. 4 minus the numerator times the derivative of the denominator. Altogether, 2x. I'm going to leave this thing factored in the denominator. If I distribute the 4, I get 4x squared plus 4 minus 8x squared over x squared plus 1 squared. Combining like terms, I get 4 minus 4x squared over x squared plus 1 squared. That's your f prime. The interesting thing about rational functions is this. If you have a rational function, let me kind of do this off to the side. R of x equals, say, p of x over over q of x. It's traditionally what they use. If that rational function is equal to 0, that's true. So is true where the numerator equals 0. In other words, where p of x equals 0. So all we have to worry about is where the numerator equals 0. Just as an aside, r of x is undefined when what happens? q of x equals 0. Good. So just kind of a couple little side notes here for us. But that makes our job for this a little bit easier, right? Because we don't have to worry about the denominator at all. We're just worried about where the numerator equals 0, and that should be something we could solve by factoring. So f prime of x equals 0 when 4 minus 4x squared equals 0. We can factor and solve this. We can use the square root property. I don't know. What works for you guys? 4 equals 4x squared. 1 equals x squared. Plus or minus the square root of 1. Basically plus or minus 1 equals x. So those are your critical points. Those are the places on the function where interesting things are going to happen. We can see that on our handout. There's a nice correspondence between that and your graph. You should check this. You've got $100 graphing calculators. It's easy to check these on your graphing calculators to make sure that it works out like this. So at x equal 1, oh, okay, yeah, we got a maximum here and we got a minimum here. Critical points are where the interesting things on a function are going to happen. Okay. Any questions on problem number 14 here? Let's try another one. Let's try problem number 16. So, a little reminder / practice with your trig functions. We've got y equals 2 secant of x plus the tangent of x. Do they restrict the domain there? They're just... No. Oh yeah, between 0 and 2 pi. Alright. So 0 less than x less than or equal to 2 pi. Okay. So actually there's no equal there. Alright. There we go. So to find the critical points, we want to think about the derivative. But before we get there, let's look at the domain here. Where is this function not defined? To figure out where it's not defined, let's realize that this is really 2 over the cosine of x plus sine of x over the cosine of x. This is not going to be defined where cosine of x equals 0. So where does cosine of x equal 0? Nice. At odd multiples of pi over 2. Remember, cosine is your x coordinate on the unit circle. So up here, 0, 1, and down here, 0, -1, the function is going to be undefined. Basically, in this interval, it's going to be at pi over 2 and 3 pi over 2. It's important to notice this because these can't be critical points. They are not on your graph. If they're not on your graph, they can't be a critical point. So you want to kind of keep that in mind right now. So the domain is everything except, pi over 2 and 3 pi over 2. If you have to write that more generally for something outside that interval, in general, it's going to look like this. Set of x such that x is not equal to pi over 2 plus n pi, or n is an integer. Basically, that's going to be all your odd multiples of pi over 2. Okay, let's get down to the nitty-gritty then. In order to find the critical points for this function, what do we need to do? Yeah, we need to find the derivative. So let's go back up to here and work here. Let me call it dy by dx. You could call it y prime as well. Those are both accepted notations for something like this. What's the derivative of the secant? Good. Secant tangent. Good. So this is 2 secant x tangent x. What's the derivative of the tangent? Secant squared. Secant squared of x. Now I want to find where this is equal to 0 or doesn't exist. So let's first of all set it equal to 0 and see if we can't solve. Suggestions on solving. What would you do? I think if this is what you mean, then yes. We're going to factor out a secant. Secant's here and secant's here, so that's going to be 2 times the tangent of x plus secant of x equals 0. So I have something times something else equals 0. One of these has to equal 0. Secant of x can't equal 0. Secant does not touch the x-axis. If you think about its graph, it's a bunch of cup shapes that face away from the x-axis. So, okay. Well, what about 2 tangent of x plus secant of x equals 0? Okay. Well, let's think about this one. This is 2 times the sine of x over the cosine of x plus 1 over the cosine of x equals 0. There's a common factor that I can factor out of here. Hamza, what is it? Yeah, 1 over the cosine of x. So 1 over the cosine of x times 2 sine of x plus 1 equals 0. You can kind of see something that's a little bit relevant here, and that where the cosine is 0, again, the function, actually the derivative is going to be undefined. But those aren't going to be critical points. Why not? Yeah, they have to be on the graph. Places where cosine of x equals 0 are not in the domain. We can't use those points. So, again, you've got something times something equals 0. There's no solution. Well, yeah, there's no solution here. Basically, it turns down to 2 sine of x plus 1 equals 0. Or 2 sine of x equals negative 1. Sine of x equals negative 1/2. Where is that true? Wow, way to go. I'm impressed. All right, so if you're struggling, you're like, oh gosh, I'm just not good at those. I don't remember those. Let me help you out. So, sine is which coordinate on the unit circle? It's the y coordinate. So I've kind of drawn part of the unit circle here, not all of it. But basically what we know is that the unit circle, the y coordinate of the unit circle is negative 1/2. So this is the line y equals negative 1/2. And you want to find these angles right here. Here and here. Okay. That's good. I want to know, where does sine of x equal negative 1/2? And maybe I just don't remember that too well. I'm looking at that like, God, my head is full of derivatives, etc. I just don't remember. What you could do is this. Rewrite this as x is the sine inverse of negative 1/2. Now, before we calculate this, we're probably not going to recognize the answer if we put it in radians. So let's put it in degree mode. Put your calculator in degree mode so we actually recognize this. And I'll do the inverse sine, so second and then sine inverse of negative 0.5, and I get negative 30. Okay. Well, then you realize, oh wait, you know, that's the negative angle. There's two things wrong. One is it's in degrees. Two is that we want it in a positive angle here, between 0 to... So if you recognize that that's a 30-degree angle, this is also going to be a 30-degree angle. Let's see if we can't come up with first this angle, and then this angle. So this would be 180 plus 30 is 210. This one would be 360 minus 30 is 330. And then you can convert both of these to radians. And this one, 7 pi over 6, and this one is 11 pi over 6. So those are your two answers. How are we looking on those two? Let's take a look at what 11 pi over 6 is in terms of a decimal. 11 pi divided by 6. A little bit less than 6. How could I check this in a different way? If I was like, you know, it just doesn't look right. How could I check it in a different way? Any ideas at all? Look at the graph? Okay, all right, cool. Hey, you know what? I think it's on our handout, right? 11 pi over 6 is about 5.8. Is there a good reason to believe that we found a critical point? Yeah. Yeah, definitely got one there. All right. Looks like you got one at negative pi over 6, which is around negative 0.5. Yay. Let's take a look at what 7 pi over 6 looks like. 7 pi over 6 should be just a little bit above pi, so 3.6, 3.7. That looks pretty convincing there too. So I think we got our critical points, and you can clearly see the points in the domain that are undefined. You've got them here at pi over 2 and 3 pi over 2. So all of that fits nice and neatly with what we see on the graph. Okay. Any comments or thoughts on problem 16 here? Let's keep going then. Time for me to give you one, and I'll give you an easy one. Problem number 12. G of x is x to the 4th minus 8x squared. And I need you to find the critical points. by looking at the graph. Line it up with the graph. Yeah, well, just choose a window that's big enough to see -2 and 2, so maybe -4 to 4. Probably what I'll try. Okay, so hopefully kind of a friendly one here. We'll start by calculating the derivative. Actually, let me step back. Sorry. You should start by thinking about the domain. This is a polynomial function. Are there any values of x that are going to create a problem when we plug them in here? No. So the domain is -infinity to infinity. Okay, that's good. So let's calculate g prime. G prime is 4x cubed minus 16x. And I want to set that equal to 0. In doing that, I'll factor out a 4x. That's going to leave behind x squared minus 4. Let's think, what else? I can factor that further as x minus 2 times x plus 2. And then from here, I can read off my solutions, right? I get a solution at 0, at 2, and at -2. So those are my critical points.
Can you use a shortcut? Just use the graph and find the next math?
You can. I mean, that would work. That would work fine here, assuming that I'm kind enough to give you a graph that has nice integer solutions. But just think about the last one we did with the secant and tangent one. You're not going to be able to trace and figure out, oh yeah, that's 7 pi over 6. I mean, even I wouldn't recognize that kind of a number. So you do need to know the general method here. Yeah, absolutely. But yeah, sometimes you can kind of trace to this. There's no problem with that. Now, let's add a little dimension to this. We're going to start trying to find the maximum or minimum of these functions on a closed interval, on an interval from A to B, whatever those points might be. So how are we going to do that? There's going to be a few steps here. So let me give those steps to you. Finding extreme values of a function. There's an ION there. On A to B. So that's A to B is your closed interval. All right, you're finding it on some small space, small subset of the real number line. Step number 1, find the critical points in A to B. Now this is the open interval. All right, so we're not worried about the endpoints. We're worried about the open interval. Second step, evaluate f of x at each critical point in A to B. Now here's the part that people miss out on sometimes. Evaluate f of A and f of B. Basically, take a look at the endpoints. Because sometimes, if you're working on a closed interval, sometimes your maximum or minimum can occur at the endpoint. You just don't know. So that's a part that people forget. And I'll tell you this very candidly and very openly. A lot of times on a test, I will create a maximum slash minimum problem like this, where you find the maximum and minimum of a function on an interval, so that one of the maximums is going to occur at a interior point and the other one is going to occur at an endpoint, because I want to see that you check them both. So make sure you check both of these as you do that, and then the last step is to choose the max or min. Choose the min or max, depending on what the problem asks. Okay. We'll start with problem number 42. So let's, I think the book writes it as y. I'm going to write it as f of x, just for my own purposes. So f of x is x squared minus 8 ln of x. First things first, let's think about the domain of this function. Is there any place you're going to run into a problem in evaluating f? What values of x are going to give us issues? Negative or 0. Basically, you can't take the log of anything less than or equal to 0. So our domain is 0 to infinity. It's positive real numbers. All right, good job. Let's work on the derivative then. F prime of x. What's f prime of x going to equal? 2x minus, good, 8 over x. Because the derivative of the log is 1 over u times the derivative of u. In this case, since we just have an x, it works out pretty nice and easy. We need to do two things here. We need to find where it's equal to 0 or does not exist. Can you see pretty easily where this one's not going to exist? At x equals 0. But is that a critical point? No, because it's not in the domain. So it's important to keep in mind the domain. I see a lot of people wasting a lot of time from, occasionally when they chase points that aren't in the domain. So I want to know where it's equal to 0. A couple ways you can solve this one. What do you see? Yeah, if there was a bracket there, then you'd have to investigate, the point x equals 0. That would then be a critical point. Yes. Good question. How would you do this one? I mean, there's a couple ways. All right, put 8 over x on the other side, so 2 equals 8 over x. All right, multiply both sides by x. So the nice thing there is that by multiplying both sides by x, on the right-hand side, I get some cancellation. On the left-hand side, this is just 2x squared. I would think that from here, you divide by 2. and then take plus or minus the square root of 4 is plus or minus 2. Okay, then what? All right, so the 1 and 5 are the A and the B, but there's a little something I'm hoping that somebody would point out about our critical points here. Yeah. It can only be the positive one, right? We don't have to worry about -2 because -2 is not in the domain. So when it comes time to evaluate these things, evaluate the function, we want to check things out at two sets of points. I want to look at the critical point and the endpoints. So 2, 1, and 5. Now here's where your calculator is going to help you out. Again, most of us, myself included, probably aren't going to be really fond of evaluating this function for different values of x. Now I can do x equal 1. That's going to be easy. That's a 1. Because the log of 1 is 1. 1 squared is 1. So that's, or log of 1 is 0. So that term disappears. But here's what you do. Plug this into your calculator. X squared minus 8 ln of x. Hopefully you've kept your calculator set the table settings. So second and then table set, so that we have independent set to ask. If not, hit second in the window and make sure that's true. With that setting though, hit the second button and then the graph key. That'll take us to a t-table. If there's some stuff there already, let's get rid of it. Let's just type in the values, 1, 2, and 5. There you go. So 1, -1.545, and 12.124. Wonderful. So we've got a minimum right there. There's your min. And here's the max. Now there's a distinction between the x's and y's. This is where the minimum occurs. This is what the minimum is. This is where the maximum occurs. This is what the maximum is. So be careful on what the problem is asking. It says find the absolute extrema of the function on the closed interval. Let's find the y, or that would be the y coordinates here. These 2 points. So there's your min, and there's your max. I will be very clear on the test what I want. If I want the x coordinate or if I want the y coordinate. How are we looking on problem 42 here? Yes? It's not a critical point. It's an endpoint. So the original problem asks us to find the maximum of this on the interval 1 to 5. So those are endpoints that are given for you. All right. Thank you. Appreciate that. Anything else on problem 42 here? Let's take a look at problem number 38. So y equals a tangent of pi x over 8. And this time we're working on the interval 0 to 2. Now on your handout, I've got this drawn over the interval 0 to 2 pi. The reason for that is I want us to think about the domain just a little bit and then be able to kind of confirm our results. Let's again go back and think about the domain. So the domain of the tangent of pi x over 8. Well, I'm thinking about that. This is going to have problems where the denominator is equal to 0. What's the denominator? If I broke this up into cosines and sines, how would I rewrite this? Good. Sine of pi x over 8 over cosine of pi x over 8. Okay. So as far as the domain is concerned, I'm worried about where the denominator equals 0. Where does cosine of pi x over 8 equal 0? And although it's kind of a small part and maybe even an unnecessary part of this problem, it's good practice here. Very good. In general, cosine of u equals 0 when u equals pi over 2 plus multiples of pi. We've seen that before earlier today. All right. What's that mean for us here? That means this equals 0 when pi x over 8 equals pi over 2 plus n pi. Let's see about solving here. I'd multiply both sides by 8. That 8 distributes itself here, here, and here. I get pi x equals 4 pi plus 8n pi. Almost done in terms of solving for x. I divide everything through by pi. I get x equals 4 plus 8n. Now, what does n represent in all this? Good. N is an integer. So those are numbers like -3, -2, -1, 0, 1, and 2, and so on. If you're to make a little table of these types of values, n and x, you'd find values like this. You'd have 4, 12, 20, etc. And you can plug in some negative values as well. -1, -4. But those are going to be the places where your function is undefined, where its domain, where we run into a point in the domain where it's not defined. Now, is that going to be a problem for us with our particular function? No, it's not. Because our function has a domain really of 0 to 2. 0 to 2. That's the domain of our function. Okay. But you can see from this graph that at x equals 4, yeah, you've got a vertical asymptote. You've got a problem with the domain. So, if you extended the view of the graph, you'd see problems at these other points. All right. Let's work on problem 38 then, in terms of finding the derivative. Y prime is going to be the secant squared of pi x over 8. That's just the derivative of the outside. What's the derivative of the inside? Pi over 8. So can secant squared of pi x over 8 times pi over 8, can that equal 0? Got a couple no's. How would you graph that? If you're looking at that going, I don't know, I'll just make my calculator do it. How would you graph that on your graphing calculator? Carefully? All right, that's a good answer. one thing I can note for you is that if you multiplied both sides by 8 over pi, all right, then this equals 0 when, basically the secant equals 0. To graph that on your graphing calculator, you have to do 1 over the cosine of pi x over 8 squared. And basically this would not equal 0. It can only equal 0 where the numerator equals 0, and 1 can't equal 0. So there's no solution. Basically, what's that saying? No critical points. Does that mean we're done, or are we out of luck for this problem? Yeah, sorry. Bad news. We still have to look at it a little bit. Where would we have to look at it? Yeah, at the endpoints. So x and y. We still have to look at it at the endpoints. Now, I'm not going to take the time here to evaluate it on your calculator. I think you can see with the values right here. At x equals 0, tangent of 0 is 0. At x equals 2, you end up with the tangent of pi over 4. Tangent of pi over 4 is 1. So, there's your two extreme values. There's your min. There's your max. Cool. Don't overlook the value of your calculator in working on these types of problems. All right. Again, let me give you a nice easy one to work on yourselves. Problem number 26. Y equals 2x cubed minus 6x. 2x cubed minus 6x. And I want you to find the extremum values, the extrema of the function on 0 to 3. So find the min and the max. Okay, so y prime is 6x squared minus 6. You know what? Well, all right, I should have probably thought about the domain here. The domain on this is everything. So I don't have to worry about any phantom critical points because I'm not going to find any. Y prime equals 0 when 6 times x squared minus 1 equals 0. So 6 times x minus 1 times x plus 1. Some of you just move that over to the other side, move one of the over to the other side and divide it and did plus or minus square root. That's fine. Interestingly, those of you who did plus or minus a square root, if you forgot the negative root, you wouldn't be in trouble in this problem. Why? Yeah, negative 1 is not in this interval. So if you're doing plus or minus the square root of 1 and you forgot the minus part of it, you'd be okay here. So we want to find the critical values here and check it out at the endpoints. So 1, 0, 1, and 3. So x equals 0, get a 0. What was this, 36? And then at 1, we'd have what, negative 4? All right, so there's your min. Here's your max. And that's it. Looking good on that one. Yeah, please.
So when you ask for stuff like this in the test, do you watch just a label with the minimum is, or do you want us to write the starting?
You know, I'll probably give you a blank to write the minimum or the maximum. So there's your minimum, and obviously here's your maximum. So, and like I said, I try and take good care to say, you know, I want the x coordinate or I want the y coordinate, because, you know, sometimes it's not clear and I don't want to, you know, try and trick you in that regard. Okay, so appreciate the question. Anything else on problem 26 here? I think there might be one more that I want to look at. And there is. It's problem number 46. So I've got the function f of x equals the square root of 4 minus x squared. And I want to look at this on various intervals. So let's figure out what those intervals are. The first interval is negative 2 to 2. Does anyone know what this function looks like? What's the graph of that look like? Yeah, it's the top half of a circle. If you can't see that, let me help out here. You could replace f of x by y, and then square both sides to get rid of the root, and then move this over to the left-hand side. It becomes positive. You've got a circle of radius 2 centered at the origin. Okay. If you solve for y by undoing this process, right here, to solve for y, you'd have plus or minus. The positive root's going to be the top half of the circle. The negative root's going to be the bottom half of the circle. So if you needed to graph a semicircle, you could do it this way. Actually, you graph a circle, you just plug in the top part and the bottom part. Okay, fortunately for us, that's already graphed. So let's take a look at it on our handout and try and answer some questions. So let's do it this way. Interval, min, and max. Okay, so on the interval negative 2 to 2, what's the minimum of the function? 0. What's its maximum? 2. Good. 2. But what if we change things up a little bit? Let's go from negative 2 to almost 0. Negative 2 to 0. Now 0, itself, this is along the x-axis, 0 is in parentheses. So again, let's think about the minimum and the maximum. So we're going from here up to, but not including that point there. What's the minimum? Still gets down to 0. But here, there is no max. You don't ever really get to a maximum. Now, mathematically, there are things we can do and say here, but this doesn't reach a maximum. You can always get closer to 0. Pick any point you want. You can always get closer to 0. You'll always get closer and closer to the maximum of 2. But because 0 is not itself in the interval, this function doesn't reach a maximum. So a little bit different for us there. Let's look at part C. -2 to 2. And part D. 1 to 2. Think about the mins and maxes on these. All right. Yeah, here the minimum doesn't exist, right? Because you never get down to 0 along the y-axis because you're not going to these endpoints. So no min. What about the max, though? 2. Max is still 2. Let's look at what happens at x equal 1, which is up here. Let's see, did that right? Yeah, I guess that must be right. Why does that look wrong? Oh, yeah, okay. It's square root of 3. So again, what about the minimum here? No min. And the maximum? Yeah, so, well, you got to go to the function. The function was 4 minus square root of 4 minus x squared, so plugging in a 1, you get the square root of 3. It's about 1.7, so yeah, that looks about right. Cool. But are you seeing this subtle difference between having the endpoint and not in terms of minimum and maximum? I mean, I'm hoping, I don't know. You tell me. Would you welcome a problem like this on an exam? Like, yeah, put about 5 of them on there? Or like, no, I don't want to see that one at all. Which one is it? First one or the second one? You don't want to see that one? You don't like that one? No?
I kind of don't get it. I mean,
Well,
I feel like there is a minimum.
well, you never actually get here. You never get here. Yeah, there's a limit. There's other stuff you can call. I'm not even going to share with you the other math terms we use for that. I don't want to confuse the issue, but there are things we can say there, but it never actually gets to that point. It never gets to its limit. It never gets to the minimum or maximum. When you're not including, say, this endpoint, you know, what is the minimum? Well, you never get to 0. Well, it'd be 0.0001, but then you can always go lower. You can divide that by 2. Go 0.00005. Well, but you never can actually get to, without x equal 2 in the domain, you can never actually get to 0. So it's not part of the range, so there is no minimum. So, likewise over here, when you get closer and closer to 0, you're getting closer and closer to 2, the closer to the maximum, but you never get there because we never quite get to 2. Did you want to ask a kind of a follow-up question, or are you just not really happy with those at all? Okay, I understand. Oh, yeah, there's one last important one that I want to do here for us. And I think it's back on the front side of the handout. Um, yeah, maybe I'll leave the front side of the handout for you at home. And let's look at problem number 4 to finish this up. And this is a good one. This illustrates a little trick that I want you to be able to do. And a big part of this is the factoring part. So it says, find the value of derivative exists at the indicated extremum. Well, let's just turn this into find the critical points. F of x equals negative 3x times the square root of x plus 1. As far as this problem is concerned, let's first of all think about the domain. What kind of problems can we run into with this function? Imaginary numbers, right? That's going to happen if this is negative underneath the square root. So basically I have to have x plus 1 is greater than or equal to what? 0. Has to be greater than or equal to 0. Or better yet, x is greater than or equal to negative 1. That's your domain. You have to have a positive value underneath the radical, and that means x has to be greater than or equal to negative 1. As far as differentiating this is concerned, any suggestions to get started with? Yeah. X plus 1 raised to the 1/2 power. What rule do I have to use in differentiating this? Product rule. Now, in applying the product rule and then cleaning it up, I'm going to employ a little bit of a factoring trick. I want you to catch that factoring trick. If necessary, we'll do another problem like this. But let's see. So, do you want me to write out the product rule, or should we just do it? Just do it. All right, cool. Sound like a Nike commercial. That's good. So, derivative of the first. Let me at least do this. So, that whole thing is our first. That's our second. Derivative of the first is negative 3 times x plus 1 to the 1/2 plus first times the derivative of the second. What's the derivative of the second? 1/2 x plus 1 to the minus 1/2. Technically, there's a times 1 there. Where's the times 1 coming from? Well done. Derivative of the inside, the chain rule. All right. Now let's clean this up a little bit. So that's negative 3 times x plus 1 to the 1/2 minus 3/2 x times x plus 1 to the minus 1/2, etc. Setting this equal to 0 and solving right here is going to be a royal pain. Let's do some factorization. Now what I'm going to do is I'm going to factor out this term here. Now you may not realize it, but when you do some factoring, what you're really doing is you're dividing. You don't see it. We don't think of it that way, but it's true. If I had 7x plus 21, all of you could factor that in a heartbeat and say, all right, that's 7 times x plus 3. But really what's going on, even though you don't see it, is you're taking each of these terms and dividing them by 7. That's what's happening. Now sometimes when the factorization gets a little bit messy, it's not a bad idea to recall this. So how am I going to do that? I'm going to factor out two things. I'm going to factor out the negative 3 and this negative exponent. This whole thing to the negative exponent. So negative 3 times x plus 1 to the minus 1/2. Now when I do that, I'm really dividing both of these terms by this. Both of them are going to get divided by that negative 3x plus 1 to the negative 1/2 term. Okay. Give you a chance to kind of catch up with writing that down. Okay. There's some nice cancellation here, isn't there? Some real nice cancellation. Let's start with this whole term, right? That whole term cancels. What else cancels here? The negative cancels and the 3 cancels, right? Getting a lot of cancellation from that term. Wow. So what's left? That'd be a plus. The 3's are gone. Really x over 2, right? So plus x over 2. I've still got the 3x plus 1 to the minus 1/2 out front. How about over here? Minus 3's cancels. But this offers another nice opportunity here. When you divide things with the same base, what happens with their exponents? You subtract. Now let's think carefully. What's 1/2 minus negative 1/2? 1. So this is x plus 1 to the first power. I don't even need to write the first power. In fact, it's gone. There you go. Beautiful. So x plus 1. Great. These two are like terms. You're adding 1/2 of x to 1x, and you're going to get 3x. So let me further simplify this. You know what, though? I want to make sure I don't have any deer in the headlights looks here from you guys. So look at me. Are we all okay with where we're at factoring? Thumbs up? Yes? All right. Thank you. So if we add those two together, we'll get 3/2 x plus 1. The negative 3 I'll leave in the numerator, but this term I'm going to put down in the denominator as x plus 1 to the minus 1/2, or to the positive 1/2 now. That's a lot healthier of an expression to try and work with. This is the derivative, and we've cleaned it up real nicely. Okay, so that's f prime. If I'm looking for critical points, there's two things I'm going to look for. One is where it's equal to 0, and the other one where it's undefined. Let's start with the easy one. Where is this undefined? Yeah, f prime of x does not exist at x equal negative 1. Is x equal negative 1 part of the domain? Yes, it is. We'll take a look at the function in a minute and see what's going on at x equal negative 1. See if we can't explain why the derivative doesn't exist there. All right, so the other part is where's f prime of x equals 0? How am I going to solve this? What do I have to do there? Let's make it easier than set the whole thing equal to 0. Yeah, basically just set the numerator equal to 0, right? This is a rational function. This equals 0 where negative 3 times 3 halves x plus 1 equals 0. So does the negative 3 affect anything? Can negative 3 equal 0? No. So really it's where 3 halves x plus 1 equals 0. No solution here. Or 3 halves x equals negative 1. Multiply both sides by the reciprocal here, 2/3. X equals negative 2/3. Okay, there's your other extreme value. Now, in a problem, you might be able to trace to that on your calculator and figure out, okay, it's negative 2/3, but, you know, quite often these points can be even more obscure than something like this, and this is a skill that I want you to have in terms of that kind of factorization. Let's take a quick look at the graph here and see if we can't make sense out of anything here, or a couple things here. Before I get to the graph, are we okay with the factorization here? Because like I said, this is a trick that I want you to have. Yes?
Wasn't our interval or our domain x squared equals 1?
Yes.
So that would still work for the negative 2/3?
Negative 2/3 is to the right of negative 1. Not by a lot,
Yeah.
but enough. Yeah. Thanks for the question. It's a good question. Let's take a look at the graph then. So let's go back to Desmos. Where did Desmos go? All right. Desmos. Start graphing. Give me a bigger graph. So y equals negative 3x times x plus 1. And I'm going to raise it to the 1/2 power. So, 0.5. There we go. All right, so we can see kind of two things going on here. Now we had a critical point at negative 1. Can anyone explain why I'm getting a critical point at negative 1? What's going on? It's an endpoint, but how come the derivative doesn't exist there? This is kind of a review from our first test. You've got a vertical tangent. So the tangent line here is straight up. It's going to have a vertical slope, and a vertical slope is undefined. What about our other critical point? Our other critical point was negative 2/3. There you go. That other critical point is your maximum. And then from there, the function just goes downhill. So, nice. Everything falls into place and kind of reinforces each other. We saw a derivative that doesn't exist at negative 1 and a maximum here. Both of those turned out to be critical points, as they should. Do you want to practice one like that again? One last one. All right. Thank you. Yeah. It's kind of like, I suppose, if we have to, let's get it over with. All right. Let's do the one on your handout then. It's a little bit friendlier than the one that we just had. So y equals 4 times x to the 3/4 minus 2x. For this one, this one gets a little tricky. You could also think of this as 4 times the 4th root of x cubed minus 2x. Actually, I shouldn't have a parenthesis there. Parenthesis here. It's tough to see here. I'll help you out a little bit. But you can't take an even root of a negative number. So the domain is 0 to infinity. So the values I've actually put into this function have to be positive. So I'll give you that much of a head start. But what I want you to do, and what I'll help out, I'll walk around, is for you to calculate the derivative and then set equals 0 and find the critical points. It's going to involve some of that factoring like we did in the previous one. You're going to have to factor out an x to the negative 1/4. You don't necessarily have to factor out something with a negative exponent. There's other ways to solve this particular one. We still want to figure out where it's equals 0 or undefined. Okay, so 4 times 3/4 is a 3. X to the negative 1/4 minus 2. There's a variety of ways you can work with this. You could solve by setting equal to 0. I wonder, though, if you did, if you would get all the points you need. Remember, we're looking for the critical points, right? Critical points include places where the derivative is 0 and what else? Doesn't exist, right? So did you get the points where the derivative doesn't exist? Right. All right. Well, let me just practice factoring out the negative exponent here. So that'd be x to the negative 1/4. I'm going to factor that out from both of these things. X to the negative 1/4 minus 2 over x to the negative 1/4, like that. Now in the first term, we get some nice cancellation here, right? The x to the negative 1/4 cancels out. Is there anything I can do to clean up the second term here? Yeah. Let's get rid of the negative exponents. This is going to be 3 minus 2x to the 1/4. Let's finish cleaning this up by rewriting this with this term in the denominator. It's 3 minus 2x to the 1/4 over x to the 1/4. And I like that. I mean, essentially what you could have done up here is you put this in the denominator and they get common denominators. That gives you the same thing. But just wanted to practice this. Now, that's your derivative. That's your y prime. I want to know where the numerator equals 0 and where the denominator equals 0. Both of those are going to lead to interesting points. So let's do the numerator equal to 0. That's going to be 3 minus 2x to the 1/4 equals 0. Or how about 3 equals 2x to the 1/4? 3 halves equals x to the 1/4. How would you solve from here? Yeah, if you want to get rid of the 1/4 here, you raise both sides to the reciprocal power. Basically, raise both sides to the 4th power. On the right-hand side, 1/4 of 4 gives me 1, x to the 1st power. 3 to the 4th is 81. 2 to the 4th is 16. So 5 and 1/16, if you wanted to look at it that way. So that's where the numerator equals 0. How about the denominator equals 0? Yeah, that's pretty clear. It's 0. Is 0 in our domain? Yeah. So you've got two critical points, right? Your critical points are here at 81/16 and here at 0. Let's see how that matches what we see when we look at the graph. 81/16, a little bit past 5. Yeah, that looks pretty good. All right, somewhere there's a maximum. What's going on here that we got a critical point? It's a minimum, and why else did we get a critical point? We got a vertical tangent there. So, nice. Anything else on this last example here? For homework, try 1 through 31, 35 through 49, and that's section 4.1.